Hi guys, in today's video we will look at a very important problem for your operations management exam, which is a job assignment problem. What is an assignment problem? It is a task to allocate different jobs to different people, ensuring the total cost is minimized. So effectively this is an operations research problem. There are multiple methods to solve these problems, and the most commonly used method and the one which mostly comes in your exam is the Hungarian method. The Hungarian method is a series of steps which are performed repeatedly until you get your optimal solution. The steps are listed above, but let's look at a problem to look at how to solve this. This is the problem you are given. This is how all allocation or assignment problems will be in your exam. 6 men are available for different jobs. From past records, the time in hours taken for these jobs by these persons are given below. The way to read this matrix is that the job 1 takes 2 rupees to complete when allocated to person 1. Job 1 when allocated to person 2 takes 9 rupees, and so on. So this is effectively a cost matrix, and this is a problem of allocating one job to one person only so that the total cost is minimized. Now how do we solve this problem? This is a series of steps which starts like this. Step 1, check if this is a balanced matrix, which means check the number of rows versus the number of columns. If they are equal, then it's a balanced matrix. In this case, they are equal. So yes, proceed to step 2. If they are not equal, then you will add a dummy row or a column with cost 0. For example, if you need to add a dummy column, you will just write 7 and then you will add a cost of 0 in every row. Then is this a minimization or a maximization problem? If this is a minimization problem, no change is required to this matrix. Proceed to step 3. Step 3 is called row operation. Go through every row in this matrix and identify the smallest element. In this case, every row, the number 1 in the 6th column is the smallest element. Subtract every element from the smallest number. So I have done one row as an example. So if you take the first row, subtract 2 from 1, 9 from 1, 2 from 1, 7 from 1, 9 from 1, and again 1 from 1. Repeat this for every row and you come to a matrix like this, where every element has been subtracted from the smallest element in that row. Proceed to step 4. Step 4 is called a column operation, where you repeat the same exercise but from the perspective of a column. Look at every column and identify the smallest number in that column. So in column 1, 1 is the smallest number. In column 2, 1 is the smallest number, and so on. In column 5, 7 is the smallest number. Column 6 you can ignore because everything is 0. Repeat the same step. Subtract every number in that column from the smallest number. So for example, the first column becomes 1 minus 1, 0, 5 minus 1, 4, 3 minus 1, 2, and so on. Repeat this for the entire matrix. Step 5. Once you have all the zeros done, try to cross out all the 0 elements in the matrix using a minimum number of horizontal or vertical lines. Just cross out. The orange highlight in this table is the crossing out. So in this case, I was able to use 4 lines, which is column 6, row 1, row 3, and row 4 to cross out all the zeros in this matrix. So I have used 4 lines. If the number of lines is equal to order of the matrix, your solution is done here. In this case, I have used 4 lines, but the order of the matrix, which is effectively the number of rows or columns, is 6. So you're not done. You need to do something more to solve this problem. You need to calculate something called as the improved matrix. Now, how do you do that? For all the uncovered rows, what I mean by uncovered is anything which you have not crossed out in the previous step, identify the smallest number. So in this case, you have row number 2, row number 5, and row number 6. The smallest number is 1. Mind you, the smallest number is not 0 because you have already crossed it out. For the remaining matrix, the smallest number is 1, identified by the green cell here. Now you need to do 2 things. For all the white cells here, which are effectively non-crossed ones, subtract this number, the number 1. So this row number 2, for example, will become 4 minus 1, 6 minus 1, 5 minus 1, 3 minus 1, and 6 minus 1. Repeat it for row 5 and row 6. Then for all the cells which are at the intersection of a row and column, which is effectively one line like this and one line like this. This cell, which is in row number 1, column number 6, is at the intersection of 2 lines which we drew. To these cells, add this number, the smallest number. So in this case, you have cell number 1, cell number 6 in row number 3, and again in row number 4, you have cell number 6. You add the smallest number. So I'll repeat this once again. For all the uncovered elements, subtract the smallest number. For all the cross elements, which is elements which are at the intersection of a line, add this number. You come to a new matrix. This is called as your improved matrix. Now, the steps after this is a repeat of what we have done earlier, which is you start again at step 5. Draw lines to cross out all the zeros. So for this improved matrix, I can use 1, 2, 3, 4, and 5. 5 lines to cross out all zeros. The number of lines is 5. The order of the matrix is 6. So I have still not come to an optimal solution. I repeat step 7, which is improved matrix. Identify the smallest uncovered element, subtract from all uncovered cells, add to all intersection cells. Come to the next improved matrix. Repeat step 5. Draw minimum number of lines to cover all zeros. Now in this case, I can cross out all zeros only by using 6 lines. I cannot do anything less than 6. So now in this case, I need to use 6 lines, 1, 2, 3, 4, and 5, and 6. The order of the matrix is 6, which means I have now arrived at an optimal solution. This problem is not yet done. You still need to do the allocation, but I have arrived at a matrix which will help me make an optimal allocation. Now we come to the last part. How do we allocate a job to a man? All the places where we have zeros, these are the places where an allocation is possible. Now you allocate every job to one man, taking into account only 2 rules. One man can do only one job. One job can only be allocated to one man. Let's take one job as an example, and then the rest can be repeated. Let's take job 1. Job 1 can be allocated to either person 1 or person 3. Now the question will be, which one should I allocate? Let's look at what other information you have for this job. Job 1 can be done by 2 people, but person 3 can only do one job optimally. He is not having a 0 in his column anywhere else. So to make an optimal allocation and ensure this person's optimization is also used, you can only allocate job 1 to person 3. If you allocate job 1 to person 1, he will be unused everywhere else. He cannot be allocated to any other job optimally. So there is only one allocation possible, which is man 3 to job 1. Repeat this for all the 6 jobs, and this is the allocation you get. Now, there could be multiple solutions in some cases. In the same problem, if you look at job number 4 and 5, I can also allocate job 4 to person 2 and job 5 to person 1. That is also the right answer. This is a solution where there are multiple optimal solutions. Now, how do we verify if all our solutions are correct? Once you make the allocation, calculate the total cost of allocation. If there is a second solution and you calculate the total cost, that must also come to rupees 22. Now that's how you solve an allocation problem. Now again, this looks like a detailed problem, but this is simple maths, addition, subtraction. If you just follow these 7 steps and repeat it until you get to an optimal solution, you solve this problem. This is a really important problem for your OM exam. Keep watching and subscribe to our channel for more such exam related videos. Thank you.